All right, today we're talking about putting numbers in perspective, which I can vary from person to person quite a bit on how well this works and on how well they can actually perceive the numbers. So the idea here is, if you look at this first example, if I'm looking at the total amount that is spent on a federal budget, and I just give you this number, 4,200,000,000,000,000, that's a great big number. In fact, that's what, trillions, I believe, because we got thousands, millions, billions, or hundreds, thousands, millions, billions, trillions. Okay, so we've got trillions of dollars here. And for some people, seeing it written this way paints a really big picture of how much that actually is. But trying to do math with a number this big can be a little bit difficult. So sometimes we'll write it as 4.2 times 10 to the what? 3, 6, 9, 10, 11, 12. 10 to the 12th power. And really it varies from person to person on which they prefer. When you're young, this would definitely be hard to recognize that 4.2 times 10 to the 12th is actually a really big number. But this might also be hard to put into perspective. But we kind of go back and forth sometimes to try and put numbers in a way that we can use them, but also to kind of help with the perspective of what you're dealing with. And again, it's going to vary from one person to another. For example, one of my sons, even though he's 10 years old, he will still say things like that he spent 500 hours on homework. And yes, he's exaggerating, but he doesn't recognize that 500 hours is way more hours than there is in a day. He says it, but his perspective, he doesn't recognize how ridiculous that is. Whereas an older kid might realize, well, clearly that's a giant exaggeration, right? So first thing that you need to understand is how to go back and forth with scientific notation. I'm not going to spend a lot of time on this because we've been doing this every year since 7th grade. So to convert to scientific notation, this is just a review. You can pause the video and read through this, make sure that you understand how that works. The second example is converting from scientific notation. Again, pause the video, make sure you understand how that works. If you need to take notes so that you remember how to do this, go ahead and take notes. All right. The other thing that we got to be careful of that you maybe have not done as much is, what if we're multiplying or dividing with scientific notation? And this is where turning numbers into scientific notation makes the math a lot easier, because right now this number is 6 times 10 to the second power, which is just 600. And it's being multiplied by 4 times 10 to the 5th power, which is 4 with 5 zeros, right? Well, if you're trying to multiply this, that might look pretty daunting. But when it's written in this form, all you do is the 6 times the 4, and then the 10 squared times the 10 to the 5th, which is just 10 to the 7th. Now, obviously, that's not scientific notation because we've got to move that decimal. So you actually get 2.4 times 10 to the 8th. Make sure that you know how to do that, okay? Adding and subtracting, we also have to be careful, because when we multiply or divide, we can leave it as 10 to the second power, 10 to the first, 5th, and we can combine those together, and we can combine the numbers together. If it's a plus or a minus in between, you have to convert it into regular form. You have to put it in standard form or ordinary notation before you add or subtract. It's not as simple as when you multiply, because you can't just take 3 and 5 and add them together and then add the 10 to the 6 and the 10 to the squared. That doesn't work. Okay. So if you multiply and divide, leave it. Otherwise, add it. Pause the video, go through those examples there. Make sure you remember how to do those problems. Hit play when you're ready to move on. All right. So some of the new stuff, and I wouldn't say it's new. It's just reviewing what you've already learned and maybe doing things in a little bit different way. But The first way that we can deal with big numbers and try to get a perspective on them is when we're comparing different numbers together. So, for example, comparing the U.S. population to the world population. If I just told you that there are 300 million people in the United States, that's a lot of people. I mean, especially when you think if you're comparing it to like how many people live in St. George, 300 million, that's a really big population. But to get a perspective on, well, how does that compare, maybe not to just St. George, but how does that compare to the world population? A lot of times we'll write these as a comparison or a ratio. So 300 million, this is the US population. In the world, there are 7 billion-ish people in the world. So I'm taking 300 million and I'm comparing that to 7 billion, which I'm dealing with millions. So 300 looks bigger than 7, but this is millions, this is billions. So 300 million, if I rewrite that as 3 times million is 10 to the 8th power. Well, it's because it's 300 million. Million is only 10 to the 6th, but we have the 0 and the 0. We're actually writing 300 million. So you get those extra 2 powers of 10. So if I put that on top, this is my US population. And on the bottom, if I compare that to the world, 7 billion is 7 times 10 to the 9th power. So a little bit of division, 3 over 7, that doesn't simplify. That's still just 3 over 7. But 10 over 8 divided by 10 over 9 leaves me with 10 on the bottom. So this becomes 3 over 70. And if I turn that into, if I divide that, 3 divided by 70, to kind of get a percent here, we end up with about 4%. Not exactly, we're just rounding a little bit. That ends up being about 4%. So compared to the whole world, the US has 4% of the population. So that 300 million that sounds so big is only 4% of everyone in the world. But if I compare the energy that we use, if you go down on this diagram, US energy is here, world energy is here. The US uses 1 times 10 to the 20th power joules in a year, and the world uses 5.7 times 10 to the 20th. Now when I simplify, I get 1 over 5.7, which approximately 1 over 5 is 20%. So we're at around 18%, or 0.18. That's how I'm getting the percent, guys. 1 over 5.7 is approximately 0.18. And I'm moving the decimal to get the 18%, okay? So we only make up 4% of the population, but we use almost 20% of the energy that gets used in the world. And that's a pretty big contradiction there. We're clearly using more than average because our population is smaller than the energy that we use, okay? So that's one way that we can compare or get a perspective of numbers, is to compare one number to another number. Another way that we do that is through scaling. And we do this a couple of different ways. A lot of times the first thing you think of is on a map. We can say this verbally, which is the first example up there. We can say that 1 centimeter equals 1 kilometer, or 1 centimeter on the map is equal to 1 kilometer in real life. You can visually see it, like on a lot of maps. For example, the one here, on this map, this distance from here to here represents 2,000 feet. And the distance from here to here underneath it represents 500 meters. Okay, so you can see it visibly on a graph or on a map, something like that. Or we write it as a ratio, which is way more common than a lot of these other ones. We actually write it as a ratio, comparing one thing to another. So we might say that 1 centimeter is 1 centimeter is being compared to 1 kilometer. The problem with scales is we want the same unit on the top and bottom. We want the same unit on top and bottom. So 1 centimeter to 1 kilometer is an okay thing to say, and visually we can look at that, but the scale ratio, that doesn't work to leave it this way because centimeters and kilometers aren't the same measurement. The degrees there are different. So for example, and then I'm going to just let you get on with the homework. If a city map says 1 inch represents 1 mile, what is the scale ratio? So it's saying that 1 inch is equivalent to 1 mile. Well, I'm comparing 2 different units, and this is hard to do with the American system of measuring things because we can't easily go from inches to miles. To change the bottom into inches, I want to change this into inches. I have to take, well, how many inches are in a foot? So I have to times by 12. And that gives me 12 inches in a foot. Well, how many feet are in a mile? So then I have to times that by 5,280. So to get how many inches are in this mile, I've got to times by 12 times by 5,280. And I end up with what? Let's do 12 times 5,280. So there are, in 1 inch, that was 63,360 inches in real life. So 1 inch to 1 mile. So again, it's okay to state that, but if you're going to write a scale, there's 63,360 inches in a mile is how you would have to say that, okay? Now, working with other systems outside the US, it gets a little bit easier. For example, 1 centimeter on a map represents 20 kilometers. So I can just write 1 centimeter is equal to 20 kilometers. If I change this into our distance notation, a centimeter represents 10 to the negative 2 power. Kilometers, if you remember that diagram from a few days ago, represents 10 to the 3rd power. Now I just have to simplify. 1 over 20 is still just 1 over 20. But this 10 to the negative 2, I want to move to the bottom and change it to 10 to the positive 2. So then I have 10 to the 3rd and another 10 squared, which means I have 10 to the 5th power. So when I rewrite this out into actual numbers, this becomes 1 on top. 20 times 10 to the 5th is just 20 with 5 zeros. So 1 centimeter being compared to kilometers is 2 million centimeters. So there's 2 million centimeters in a kilometer. So my scale would be 1 centimeter to 2 million centimeters in the real world. So I think it's a little bit easier when we're converting with kilometers and centimeters and gigabytes and decabytes and all these other forms than it is when we're dealing with inches and grams and pounds and different things that way. So your homework is, let's see, what are we doing? We are on homework 3B, I believe. Homework 3B. As you're going through that homework, there may be a few units. I noticed there was a couple questions that just assumed that you knew how to go from grams to pounds. I don't have that memorized. I don't expect you to have that memorized, but there's some questions that if you don't know the unit conversion, go ahead and just look it up. We will work on this in class. So if you're planning on being in class, we'll do these problems in class. You can ask questions. Otherwise, do it at home. If you have questions, you can email me or come by the room.